Okay. So now let's talk about once we have the nucleation, the second step would be so-called growth. Once we form that tiny crystal everywhere, either homogeneously or heterogeneously, the next step would be growth for that solid to become larger and larger, eventually converting all the liquid to solid. And the simplest one, let's first deal with pure element, pure aluminum, pure silicon, or some other pure ceramics. Okay? Of pure element solid growing out from its liquid. Okay? To, before we do that, let's first think about the interface. As we mentioned before, there are two types of interfaces between solid and liquid for pure element. One type people call it diffuse interface. One side solid, the other side liquid. Diffuse means atomically. At the atomic scale, the interface is like this, zigzagged. One atom up, one atom down, another atom up, another atom down, zigzagged. And people find that these types of interface for the system that satisfy roughly this relationship. What does Tm mean? Melting temperature. What does Lf mean? The so-called latent heat for fusion, which is how much amount of heat when liquid goes to a solid, it is released out. Latent heat for fusion. If this ratio is roughly R, actually this ratio, remember we did it earlier, is essentially the entropy change. The entropy change from liquid to solid, if it's roughly R, gas constant, then these types of material, they would have so-called a diffuse interface, which means microscopically at atomic level, it's diffuse, not flat, going up and down, zigzagged, okay, at atomic scale. And then microscopically, micro means large, over microns, over even millimeters, they would be flat or branch-like. That's what people observed. And it occurs for most metals. To give one example, nickel, Tm, melting temperature roughly 1455. That's a typical metal. And it has the FCC structure, face-centered cubic structure. And if you go into the literature, you can find what? Latent heat to 98 kilojoule per mole per kilogram. And if you know, of course, you know the atomic mass for this material, you can go change from kilojoule per kg into kilojoule per mole. Make sense? You know the atomic mass. And on the other hand, remember this is what structure? Nickel. FCC structure, what's the coordination number for FCC? 12. Okay. Based on this, remember earlier when we were studying in the second part of surface energy, once we know the latent heat and the coordination number, we can kind of estimate. Before that, we were doing sublimation, but we can kind of estimate. Due to this coordination number, we would get a low bonding energy. The bonding energy is not very strong for nickel. Okay? And as a result, they have diffuse interface, the growth. Growth of what? Growth of solid nickel from liquid nickel would be so-called continuous growth. By continuous, we mean at atomic scale, we are randomly adding atoms across the interface, randomly. It can happen here, it can happen here, can happen here, randomly, pretty randomly, but also pretty uniformly. Okay, the growth of solid into the liquid by adding individual atoms randomly at an interface. This is one type. The other type is, remember we said something like this. Between the solid on one side and liquid on the other side, it's pretty flat. How flat? Atomically flat, which means over many atoms is very flat. Okay? And these types of interface would occur for the material that is satisfied this relationship. The latent heat divided by the melting temperature is roughly on the order of 4 times of gas constant. I'll put it another way. The entropy change, delta S, is much larger, 4R. Okay? And for these, we said it's microscopically flat, atomically flat. And for those, if we observe their growth, they quite often become stepped or zigzagged feature for their solid when you observe. But at each zigzag is atomically, microscopically flat. And it happens for material such as silicon, germanium, or many of the non-metal material. Again, look at one example. We're looking at what? What melting temperature of silicon? Silicon, okay? Melting temperature very close to, very close to nickel. The latent heat would be, well, pretty high, right? Pretty high, kilojoule per kilogram. And if we know the atomic mass, we can go to kilojoule per mole, and we know the coordination number. Make sense? And based on this, we can, the consequence, of course, we are not dealing with sublimation, but the consequence is similar. They would have much higher what? Bonding energy. The comparison here is, okay, you have this much kilojoule per mole, and it's bonded so many coordination number. You have even higher bonding energy per mole, and your coordination number is lower. As a result, of course, the bonding energy per bond will be much stronger between what? Silicon and silicon than between nickel and nickel. Because of this, they would experience so-called lateral growth. Lateral growth. And what do we mean by lateral growth? We mean, okay, the growth, you are adding atom not randomly, uniformly, but only at what? Specific locations. You cannot add atoms randomly as you wish. You can only add atom at specific locations. Those types of growth of pure element solid into the liquid, people call it lateral growth. Okay? And then we give some